So, today we have this problem. Now, it could be solved in a really easy manner, but I solved it in the worst manner possible, only then I found the easy way, so I'm gonna review the hard way purely because it's more entertaining, I guess. Okay, so this hint over here is useless in the unnecessarily complicated way. Okay, assume that phi is a linear transformation in vector space E, such that phi composed with psi is equal to psi composed with phi for every linear transformation of psi. Yeah? I have to prove that phi is basically the identity map multiplied by a scalar. Okay. Now the way I went about it is I said, well, phi of okay. First of all, let's say that v of alpha belongs to capital A. This over here is a basis of E. Okay, now that we have this sorted out, any x and E can be represented in this manner as a sum. How do we call it? Well, it's important, not really important in this part, so I won't define it like that. Or look for cool Greek letters to apply. Let's just jump straight ahead to defining the find psi for bases as arguments. So let's say we have v of n, right? And we take the function phi. So what this should equate to is, well, the general form of a vector is a sum of, well, a sum we're using the basis. So what we're gonna do is we're gonna rewrite Vn as some sum. Mostly not really important per se. Yeah? The important is what we get after is some vector in E. This could be represented in this way, yeah? And let's add n here to specify that the coefficients are specific for v of n. Okay, now we do the same for psi, yeah? But we pick another sequence. Well, let's start with data. Let's call that sequence xi. So what I initially did next was I wrote out the compositions and then said that they're equal, and got some really big and scary thing, but it did work out eventually. Okay, so let's compose this stuff now. Phi composed with C for now of V of n. So the reason I'm reviewing the basis related stuff is because the rest can be constructed through it. Okay, so we have phi of now. Let's grab just this over here. I'm not gonna rewrite it, it's the same. And now for the phi, yeah? First of all, we can bring out the sum and get sum through alpha belongs to big A. I won't write it down because I'm lazy. Xi alpha n. We have phi of v of alpha, and now that's something we can work with too because we have defined for Vn. So sum through alpha C of n. Now let's use B for this sum. It also belongs to capital A. I'm just, well, separating stuff so it doesn't like coincide. Okay, now let's look at the definition of phi. Here it is. Sum through B, and next we're gonna have data. Instead of n here, we will have alpha. Instead of alpha, we will have B here. And VB. Now let's just rearrange let's rearrange a bunch of stuff. We can bring the C inside here. Then we can swap the sums and get some that is more form of like really any vector. Okay, here we have C, alpha, and else do we have? Theta, alpha, and B here, and VB finally. So this is gonna be the coefficient over here. This will be useful in a second after we express in a similar way the other composition. It's a really similar process. In fact, I don't want to write it down because, well, if we were to look at the way I defined phi psi for Vn, you could see that they are basically the same except Xi and data are replaced. So what I can do is I can do just a bunch of symbol juggling and get a thing that is basically the same, except here I'm gonna replace data and Xi. I'm gonna make them be vice versa. So here we'll have instead of Xi with the n and alpha, it's gonna be Xi with the alpha and B. And instead of data with alpha and B, it's gonna be data with the n and alpha. Let's just go through this quickly just to make sure it works in a similar manner. Here we'll have the data instead and C here. So next we bring stuff out. Still data here. Okay. Next we'll get a sum like that here with the C being dependent on B. Okay, yes, it seems like that. Now what we're gonna do is we're gonna say that, well, these things are supposed to be equal, right? So when we subtract one from the other, we get 0. And now let's actually proceed and do that. So we're to write it out. We get this interesting sum. Essentially, all the sum notation gets like passed through, and afterwards we begin with this one. Okay, let's copy paste this part and subtract this part. VB equals 0. Now, mind you, we're just iterating for like vectors that belong to the basis, and all of that is equal to 0. So this coefficient over here is supposed to be 0, always 0, because we're working with the basis. So let's go ahead and say that. This over here is always gonna be equal to 0. Okay, now let's go ahead and bring out some parts of this sum that could be of use for us. Primarily, B and N are of particular interest to us, so say alpha is not equal to n or b. The rest of the sum holds like usual, and then we can add stuff back. So xc, let's begin with n. When we substitute n for alpha, we get xc n times theta and b minus xc okay, what we have here, alpha is going to be n b times theta and n. Okay, and now for the b part, it's really similar. Now we get c and b here times theta bb minus we get c and bb times theta and b. All of that is equal to 0. Now notice after that none of the parts of this sum gonna be dependent on data n, c and n, data n b, c and b, or data bb or cbb. It's never gonna show up here after we have secluded it. So let's replace this with some, well, not really a constant, but it sort of is a constant dependent on, well, b and the rest of the sequences. We'll just call it some letter. Let's call it letter t for now. It's not really a constant, but you get what I mean. I just don't want to write it out every single time. And now as for this one, we can kind of group the stuff. We can get we can notice that, well, some sort of coincides. For example, NB here, and NB here. So let's go ahead and apply that. Plus theta NB times C and N minus CBB. Okay, plus now we're gonna do the same but for C and B. For the positive term, we're gonna have theta BB. And we subtract theta and N and get 0. Now, what I'm gonna do is I'm gonna assume a few things. First of all, this and this is completely independent together. Now, this and this is gonna be independent given that n is not equal to b. And a similar case for this part. So let's review two cases. N is not equal to b. Then this and this is independent. This and this is independent. So we can just label a bunch of letters here and we can modify them however we want with 0 repercussions. So t plus theta and b, let's call this part epsilon, plus c and b, let's call this part dependent on theta delta, equals 0. Now notice how this c is completely separate from the rest of the world. So notice how we were working with any linear transformation whatsoever. That means that if c were to change, this is still supposed to be true for any c and b. So let's go ahead and apply some change. Let's say that we substitute c and b with c and b plus c delta 0. Now we distribute stuff and the rest that we have is c times delta equals 0. Now we can add some non-zero c, and this is equal to 0, therefore delta is equal to 0 for sure. Well, delta is equal to 0, so data bb minus data n equals 0 for every b. Now, that is given b is not equal to n. Now notice, if we were to substitute that b is equal to n, then this would be 0 anyways. Because, well, data bb is equal to data bb, no wonder. So we can get rid of this condition part and just say that data bb is equal to data nn for every b that belongs to capital A. And, well, for every n that belongs to capital A. That means that, well, oh, this is some constant. Let's call this constant. Let's call this constant lambda. Okay. Now, after we have done that, we just need to show that, well, not really show, let's just work with this part. After we have shown that. So we still have this part left, right? The one that we labeled data nb epsilon. So essentially, let me remind you real quick that the thing I was talking about is this problem. We're working with proving that this is basically just color times identity map. So for every data where n is not equal to b, this is supposed to be well, 0. So let's show that it is indeed supposed to be 0, right? To work on that, let's first review two cases. N is not equal to b, and n is equal to b. Say is n is equal to b, then, well, c and n minus c and n is gonna be equal to 0. So this entire thing is gonna be equal to 0, and again it just returns to this basis part. So we have to show that t is equal to 0 for this part, and, well, it's fairly easy. If we were to go over here, and, well, we were to substitute b for n, then we just get to practically equivalent. Oh wait, no. Okay, I'm just jumping ahead of myself. Let's review the case where n is not equal to b, and it will help us review in this case. So n is not equal to b. Now, again, this is some modifiable part, epsilon. We can deal with it however we want, in any way. We can just add some c to disk c or disk c, right? And this will change, so clearly data nb is equal to 0 for every b and for every n, or every b not equal to n. Okay, so we have deduced some things. And now, if we were to go ahead and check if the basis is 0, well, wait, no, it's already implied, Okay, I'm just being stupid, It's implied because we're already told, that this is true. We don't have to prove it, we're just trying to show what comes from this equality. I don't have to show anything whatsoever. Okay. So, we have shown this. We have shown a bunch of other stuff that is also useful. When n is equal to b, then, well, we don't really need any more conclusions. But when n is equal to b, we're to go ahead and substitute stuff in, then the rest of it we have is this. Okay, yeah, it seems to work out a whirl. We'll just go ahead and well, n is equal to b, data is going to be with two like equal parts, and it's going to be equal to that constant lambda. Yeah, okay, it works out. So this method overall is overly complicated. I told you that it's horrible. There is a simpler way to deal with this problem. It's like the first thing I have actually done prior to finding the easier one. So I decided to show it because I thought it's like far more interesting in a way. Okay, yeah, so in the end we have deduced two relations for every n, theta and n is equal to lambda. For every n and for every b not equal to n, theta and b is equal to 0. Now recall how phi is equal phi over vn is equal to what? To this. Just copy paste it. So let's grab the sum and separate it. A is not equal to n, and theta n alpha v alpha plus theta and n vn. Now recall how this is going to be 0. This is going to be lambda, so we have lambda vn. Okay, now let's grab a general vector x of E. Let's express it with a sum. For the letter here, let's pick pi for the sequence. P alpha, V alpha. Okay, now we were to grab it and plug into phi. Phi of x is going to be the sum for alpha, P, alpha, phi of V alpha. Now that's just going to be lambda V alpha. We can grab out the alpha and pull it outside of the sum. We have a sum for alpha, P alpha, V alpha, which is just x. So for every x is going to be equal to lambda x. I mean, I have shown it now, but that was really complicated. There's an easier way to do that. You could just grab a random coefficient from the vector and say that the function psi is equal to that coefficient of the vector you feed it times some constant vector, and then it's easy to show that phi is just lambda x. But I have done it through this way. It was midnight when I was actually trying to solve this, so I guess you could say my brain was deficient at the time. But that's it for today. Bye.